Yeah.
Okay, cool. So welcome everybody to this session, and I apologize last week we couldn't hold a session because of the heat wave. My schedule has been a bit travel schedule, let's say, a bit upside down. Because of the disruptions of the heat wave. I think everyone has, at least in the Western Hemisphere, must have felt it. So welcome to session 11. And today, this is the agenda. We'll start with the pre-lecture comment stuff, to go through the timeline stuff. And then I will make the announcement just briefly for those who haven't seen the newsletter or, have attended the previous discussion. The new course of measure theory, measure theory and functional analysis, which will start next month, towards the end of next month. So after that, we'll go direct to the main session, which is to deal with this thing called case cycles. And then we go through cycle notation. As I was saying before we went live, is very often I've seen people introduce the cycle notation first and then introduce the concept of case cycles. I think the other way is actually much more easier to understand, to start with the abstract and then introduce the notation later. Then that way is not confusing, I think. Anyway, let's see how what's your verdict. So, okay. So welcome to session 11 again, as I was saying. So this is the timeline, more or less, for those of you. I know we have extra people watching on YouTube, people emailing me. So before this topology and differential geometry, there was something else called foundational. What was it? Foundation module, I think. I even forgot what the title of the course.
I think that's what it was called, the foundation module.
Yeah, so it's essentially like a kindergarten linear algebra stuff, finite dimensional vector spaces, in particular Hilbert spaces stuff. And then after that, we did this topology and differential geometry crash course. The whole purpose of that is because we wanted to do a course on Lie groups and representation theory. But before you understand what Lie groups, because they are not just algebraic structure, Lie groups also have smooth structure. So that brings us to the realms of topology and differential geometry. So we needed to have that to have a good understanding of the basic understanding of what smooth structures, smooth manifolds are, and then the way the group structure and the manifold stuff interact with each other or they coexist together. This is something that we will do here. And in the middle, we will have, so we decided to start here, and then in middle, the idea is to have then a refresher on group theory. I know a lot of you have some of you had a crash already have already been exposed to group theory before. So this is a kind of a refresher. But one of the advantages of doing this is that I tested a new format, because the feedback I got from the first course was the first two was that things were very abstract, so it would help people if we have some, after going through the abstraction, have like concrete use case stuff. So in this group theory stuff, so far we have done I guess pretty well with that, because we cover some important notions like cyclic groups, and then we've shown how cyclic groups are applied in concrete stuff, in this case in cryptography, in the case of the Diffie-Hellman key exchange protocol. And we will have another one. Our friend here on the audience, Bob, will do another one. We will talk about that at some point once we cover the notions that he needs before he gives his applied talk, which is, I think he needs orbits. Bob, what do you need again? I always forget. You need to know stabilizers. You need the notion of orbits, all these stuff before he can give us a presentation. Yeah, orbits and the stabilizer. Yeah, we are getting closer to that. Okay.
And it's been implied, but the idea of the group action as opposed to the abstract group.
Yeah, this is something that we will, thank you, George. We will do this actually in the next session already. We will talk about actions. Yeah. And then we'll see how it connects with some of the stuff that we've been covering in the last 2 sessions, even today as well. So yeah, we will most likely have 20 lectures, because I'm actually, as you can see, I'm trying to drag my feet because this could be my last course. It could be. Let's see how the other format goes on, because we are getting to a point where my work commitment is making it very hard for me to keep delivering courses. So this could be my last end-to-end thing. But it doesn't mean it's like my last involvement in the whole thing, in the whole community stuff, because I will still get involved with the courses that we have planned on working on the curriculum, and also on finding out the people to deliver the courses if I'm not able to do them. Eventually, what we really want to do this is to make it like, pretty much like a community run thing, where people like yourselves, I will probably start, I'm floating this idea of nominating ambassadors, something like that, or whatever title I call it, for those of you like George and, the others and right now who have been with us for some time, whereby, you can go and talk to the community and then suggest what course the community wants. And then, we can work out, what to deliver, how to deliver the course. Yeah, so something like that, as opposed to just things coming internally. At some point, we will make this like a proposal-based stuff, where the community members propose, look, we want to learn about this, because of that. We'll say, okay, yeah, let's have a course about this. So that's where things are heading. Okay, so Lie groups and representation theory will definitely happen as well. The question is, it might overlap with the new course on functional analysis and on measure theory stuff, but I don't think it will be a problem, because we will have a bit of a head start with the measure theory stuff ahead. So I'm looking probably the Lie groups and representation stuff to be probably around September, I would say, maybe. Let's see how it goes. Possibly October, I don't know. I'll send a survey for you guys to see. And I already have another person who, in principle, could be doing this, another fellow mathematician. We'll see his schedule, and then we'll send a survey and see. Yeah. If he cannot do it, I myself, I will start it. And then when his schedule is available, he can, take over me. But yeah, let's see how it goes. So it will definitely go ahead. So it's not like I know Dimitri was asking what about when we announced the measure theory and the functional analysis course, it was asking. Yeah, so Beran is asking, what are the suggested time slots for this? This is the thing that we need to figure it out. Whether, because James is the measure theory. I will come back to this question once I go through this, the measure theory stuff. Yeah, but before that, so just to recap, before we go to the course announcement. So this is where we are. We're still in groups. We are talking about symmetric groups. We are getting closer to getting into the matrix group stuff, which is the bits that we need in order to wrap up the course. Now, as I was saying before, we do have this thing locked, this measure theory and functional analysis course. And the start date in principle should be Monday, August the 29th. And it will consist, we will have a question and answer session maybe 1 or 2 weeks before this starts, so you can come and ask questions, because we're still adjusting some of the stuff, the curriculum stuff, but not major changes really. So the idea is that we'll have like pre-recorded lectures. So far, basically what we've been doing is having like bi-weekly lectures, live sessions, and you get some challenges, and then you have study sessions and so on. So what we are trying to do with this is to see whether we can have like a pre-recorded lectures released few days ahead of time before the discussion or study group sessions. And together with that, you will have also on top of that, like office hours with the lecturers and these things, There will also be problem sheets, and then the problem sheets will be released after the discussion stuff. So it's a new format. And if the community members, those of you who attended, think it's like the right way to go forward, we will start rolling this thing out to the other courses, including the Lie groups and the representation theory stuff. Otherwise, maybe we can keep the Lie group and then leave the other one like, with the new format. It could be a way of, consolidating the two. So it's not like people are not like having to be like, in this thing position of every week, like being, having to attend two things at the same time, So maybe it could be the case that we'll maintain the Lie group stuff bi-weekly like we are doing now, and then the other stuff, with the new format. Yeah. So what do you think so far, George? What do you think about this idea?
I'm curious to explore it. I actually like the idea of more structured problem sets.
Yeah.
Because we'll be getting into the more advanced material.
Yeah. I agree with that, and I think especially because we want more hands-on stuff. These are things, some of the stuff that because of my limited time, that I wouldn't. That's why we hired James to do this. James, yeah.
And the problems really tie the abstractions to intuition and to applications.
Yeah, correct. Yeah. So in the end, it might make the journey a little bit more easier. Yeah. So the lecturer will be for this measure theories and functional analysis will be James Heffers. I hope I pronounced his name correctly, but we'll have a Q&A with him so he can correct us. And he's already on Discord. So there is already on the Discord channel, we do have a channel already called what's the name of the channel? I forgot. MTFA, I think. MTFA course. Obviously, this is abbreviation for Measure Theory Functional Analysis course. Yeah. So James is already on Discord. If you want to have any question, you can just ping him. But I would suggest that you hold on until we have the Q&A session with him. And the schedule will be more or less like this. Lecture 1 will be about reviewing calculus and analysis. In fact, in the Discord, that's why if you are watching this, you want to take this course, you really need to join Discord, because James will be sharing some materials, like a refresher stuff on calculus and analysis that, it will be helpful for you to review before the course starts, even though he will do some brief review of it, but it's really helpful if you go back again to calculus and the real analysis, especially integration theory, and then from lecture 2 to 5, you'll cover the notions of sigma algebras. This is where those of you who have taken topology, this will be very, very useful if you review the axioms of topology, because, you will see this thing of, a sigma algebra, for example, the axioms will resemble pretty much, will be very, 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 very close to topology. In fact, the way one constructs algebras very often, sigma algebra is very often to use an existing topological space and use it to construct an algebra, a sigma algebra. So yeah, go review the lecture 1 or 2, or in fact, I would say the topology and differential geometry course, you should probably review lectures 1 to possibly 4, I would say. Where do we touch Hausdorff stuff and these things, and even the metric topology and this type of stuff. Yeah, review everything before manifolds, really. That will be very, 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 very useful. And then after that, yeah, we'll have the the axioms of measure. You will see actually how probability, this is what Kolmogorov used to to give a formal definition of probability. So he uses measure theory, the language of measure theory. So we'll know what the probability measure is, these type of things. I think we did cover this a little bit in a superficial way in the foundation module, in the set theory. I think in lecture 1 or lecture 2, something like that. So anyway, then we'll go to things like outer measures, Borel measures. This is very important, especially for quantum stuff. You will see this later. We'll comment on this after. Measurable functions, and then you go to all the way to seeing the difference between the Lebesgue integral and Riemann. And then finally we'll go to Hilbert spaces and operators, blah blah blah, all this. Okay, so there's a lot to be covered. This is really a great opportunity for you really to start again and get how to deal with the infinite dimensional Hilbert spaces. So if you are interested in stuff like a continuous variable quantum information theory, for instance, all this stuff, this is all like these things. This is all like all this mathematical stuff that you learn here will be very useful. And also another thing is, this will be the foundation for another thing. We will, after this, James will come back. We will do something on operator algebras. So this will be the next level, operator algebras, which includes C-star algebras and so on, because after that, this then means you have the baseline for us to cover what I promise you, which is non-commutative geometry. Without this, you will not be able to follow that. There's no way you can get any closer without this. So this is a very important module, for you to step up to operator algebras and then be able to make the jump to non-commutative geometry. Okay, so that's it. I know we've been talking now for some time. Don't worry, we will not run over time. I promise you. Okay, so before we start, actually, does anyone has any questions about this?
The chat looks quiet. Oh, here we go.
I mean, the whole purpose of giving you access to this, I really believe that, yeah.
Dimitri has a question.
Yeah, you will see this actually. We will come revisit once he touches the Hilbert spaces stuff. We will see for example, in quantum mechanics, the space, the space that the Hilbert space that who was using it? This Hilbert space that Schrödinger was using, the space big L2 of R2, for instance, which is the space of square integrable functions, which is the space where the wave functions of Schrödinger live. That Hilbert space, square integral in the sense of Lebesgue, but to get to Lebesgue stuff, you need measure theory. So that's yeah. Go ahead, George. You wanted to say something?
Dimitri had a comment that it has always struck me that the probability formulation of quantum mechanics does not use a measure theoretic approach. So therefore, he's curious to see how it ties in.
Well, yeah, not directly. It's behind scenes, the machinery, like the Hilbert space itself. For you to deal with the operators and all these integrals that show up, you will need measure theory. Yes, it's in that sense. All the operators that will show up in the thing when you deal with the infinite dimensional Hilbert spaces, which is what physicists deal mostly with, especially when they are working with non-toys systems like the harmonic oscillators, all these complicated systems.
I think maybe, and this is maybe my prejudice, the physicists are less interested in mathematical foundations and mathematical rigor and more inclined to just get on with it, as they say, shut up and calculate.
Yeah, but behind scenes, obviously, very in history, mathematicians come in to clean up the mess. A typical example of that is reminds me of Richard Feynman, where he introduced this thing called the path integral, which is like a horror to mathematicians and these things. And it took several years for mathematicians to actually. It works in the calculations. It ended up yielding the correct results, but it's like it's like if you ask a pure mathematician back then, when you look at it, they'll say, what is this? It's like it's complete nonsense. Yeah. Anyway, Dimitri, you will see one of the things that we will do as we go through this course, especially when we reach to the operators, section of the thing. You will see more of this, especially in quantum mechanics when we start. We will revisit the axioms and revisit some use cases in some physical systems. Especially the ones that have like where you have to consider unbounded operators, for instance. Yeah, so it can be very tricky. We'll come to that.
I think it would also be fair to say that most probability and statistics courses really don't go into the Kolmogorov foundations.
Yeah, they don't. They just skim through the thing. They still do the things in the old school way. I still see even in machine learning courses nowadays. The way a lot of people, they don't really take this rigorous approach to teaching probability theory. They just go the old pre-Kolmogorov type of approach. Yeah. Okay. So anyway, let's get to the session. Don't worry, we only have 2 things to cover. So we will finish probably in 10 minutes. Okay, so I hope I haven't made any typo. So the first definition is the notion of case cycles. Okay, so in here, I'm using very unconventional, instead of, as I was saying at the beginning, before I walk you through the definition. Normally when people before they introduce the notion of cycle, they introduce the notation first, through examples and so on. I'm starting in a very abstract. I think this is probably the best way. Let's see your verdict. Because then all the notation stuff that you come up with later, you are hit with, will become like a natural consequence of this. Okay. Okay. So let's X be, let's say, the set with n elements, 1, 2, 3. Okay. 1, 2, 3, n. Okay. To n. So a permutation, that I call, this is just my notation, okay? This is not standard notation. This is just me to make it, I'm trying to be very helpful. Let's see whether this is the case. At the end, I will ask you whether this was, especially the ones who have been exposed to this before. I will ask you your verdict. So given a permutation, you know what a permutation is, which is an element of the symmetric group Sn. I will call it sigma tilde. This is called a case cycle. Okay, it's called a case cycle if there exists a subset. So there must exist a subset, that I labeled A1, A2, A3, to AK with exactly K elements here, which means that there are no repeating elements. So it's like it has exactly K element.
Is that a strict subset, K less than N?
It could be the entire thing. So it doesn't have to. It could be the entire set itself. Yeah. What's important is that they have to be distinct elements. Yeah. So it could be the entire set itself. I mean, the entire X itself. Okay. So this is called a K cycle. So it's not just so K cycles are are a special type of permutation. The first condition they need to satisfy is that there must exist a subset A1, A2 to AK. So there must exist some elements of the set X, a K number of them, okay, that makes such that this thing behaves like this. This permutation then behaves like this, okay, this sigma tilde, okay. So the first thing that it does is, sigma tilde of AI equals AI plus 1 if I is less than K. Okay, this is to say, if you imagine these elements like lined up together, if you pick one of them, if the index I is less than K, what the permutation does is it takes it to the next slot. Okay, so this is what it's doing. Okay, so this is in the case when I is less than K. And then it does something very interesting here. for the last element, in the index, indexed element, in indexed element. So this one, AK, sigma tilde of AK takes you back to the first element. Okay, you start to see why the name cycle. We'll see this in a specific example. This is very abstract at the moment, but you will thank me before, because with this you can, you will thank me after, because with this you can generalize. Okay, so this is something interesting it does. So it takes the last element, it cycles it back to the first element, and then it does nothing to all the other elements. This is what this formal stuff is telling us. By the way, can you see the cursor?
I don't see the cursor.
Okay, so it doesn't matter anyway. So condition 3 means that it does nothing to the remaining elements of the set X. Okay, so it does nothing. It only messes about with these guys. So that's what this thing does. Okay. Now this is a naming convention. This subset is called the support of the permutation sigma tilde, and we write sup of a tilde to denote that. Okay, we will change the notation in a minute when we come back to the cycle notation, but for the time being, let's stick with this. Okay, and then here's a very important thing, definition. When K equals 2, then a 2 cycle is known as transposition. Okay, we'll see an examples of this. So a transposition is just a 2 cycle.
Kind of an aside is
and
that.
Then another definition. Yeah.
Is the term support related to?
Go ahead, George.
Oh, I'm sorry. Just an aside, I'm asking if the term support is related to, in analysis, you talk about functions with compact support. Or is that a coincidence? That doesn't really matter.
It's a coincidence. Yeah.
Okay.
Let's say it's a coincidence. Yeah. Okay. So this is how so for K equals 2, this is called this is a 2 cycle. By definition, right? It's K cycle, right? It means that there is a subset of 2 elements that are exchange with each other, but then all the other elements are left unchanged. Okay, so this is known as transposition. I hope I have I got it correctly written. Okay, and then this is an important definition. Now let's suppose we have 2 cycles. Let's call it sigma tilde 1. In this case, it's a K1 cycle. So this is a positive integer. Okay, and then we have a second cycle, which is sigma 2 tilde, which is a K2 cycle. Okay, then we say the 2 cycles sigma 1 tilde and sigma 2 tilde are disjoint if the corresponding supporting sets are disjoint. Okay, so if these 2 sets, the corresponding sets, the support sets, their intersection is empty. You will see this in a thing. This is very abstract, I must admit. Okay, but this is the 2 things that you need to think about. Okay, so to recap, a K cycle is not just any type of permutation. Okay, it's a special type of permutation. It's a permutation that must have some elements of X such that it behaves this way. Okay, K elements. Okay, for it to be called a K cycle. Okay, for it it must satisfy this. It must behave this way. So if it doesn't, then it's not a K cycle. Okay, now let's jump into examples. I know you are all craving for examples, so let's see. I hope it didn't backfire. What's your verdict? Going abstract or starting with the cycle notation? What's your verdict, George?
Well, I come down on the abstract side of the fence, but that might not apply to everybody else.
Okay. What about anyone else before I move to concrete examples? for everyone to start smiling. I think this is much more, for me, the reason, normally people start with the cycle notations. I've seen that a lot. They start with the cycle notation, and then they introduce the concept. This is a 2 cycle, this is a 3 cycle, this is a thing. I actually think it might become very confusing, you know, even though you go through a lot of examples, see where are these rules are coming. Yeah. Yeah, so Berend is saying abstract as we can test this against our understanding. Yeah, exactly. So you can, you know, generalize and so on. Yeah, thank you. Obviously, there will be a bit of annoying, something annoying because we'll change the notation again. But nevertheless, you can always come back to this and refer to you if you are confused. Okay, refer to this. This strips down all the stuff. Okay, all the non-essential stuff. Because normally concrete stuff come in with all sorts of dressing, all sorts of distractions, you see. that's the thing. Okay, so let's see our examples. I hope I didn't make any typos. That would be a good thing. You know, I took some time to do actually the diagrams. So let's consider examples of 2 cycles. In this case, we pick S4, okay? Can you guys see? George, can you see? But sorry, some of the stuff are very small, but you know, you can maybe try to zoom.
If I go to full screen, I can see it.
Yeah, can everyone else see it nicely? Before I walk you through this.
Actually, the text is very small, the subscript.
Yeah. Yeah, sorry for that. I think in the study groups, once you get hold of these slides, the PDF, then you'll be able to zoom it and see it. So in the meantime, I'll try to walk you through. So in this case, we have S4, which means that we are dealing with a set with 4 elements. Okay, and this has 24, as we covered last time, as you must have figured out. For S4, the symmetric group S4 has 4 factorial elements, right? Permutations. In this case, 24. Okay, so in this case, consider the following permutation given by the 2-line notation, and I also added a bit of this thing. This will give you a bit more. I took some time to do this. It was a bit of a pain in the backside, but I hope it's worth it. So let's consider this permutation sigma 1 tilde, which consists using the two-line notation. You see the arrows go down. I haven't removed the arrows just to make it easy for you. So this permutation takes 1 to 2, takes 2 to 1, but leaves 3 and 4 untouched. Okay. So in other words, it takes in a thing, it takes 1 to 2, but then it takes 2 cycled back to 1. So you start to see why the name cycle, where this name cycle. So just as a heads up, just to help you, when we deal with cycles, you know, you ignore anything that's not touched. The things that are untouched, you just ignore them. You only focus on things that are changed. You know, that's where you focus. Wherever the changes start to happen, this is where, you know, the cycle stuff starts. Okay. Just as a thing, okay? And here's the second. So the claim is that this sigma 1 tilde is a 2 cycle with support 1, 2. Do you agree? You look at the definition. I will go back again to the definition. Right? So it takes, so in this case, you know, A1 happens to be 1, A2 is 2. Right, so it takes A1 to A2, but then it takes the A2, which is the last element, back to A1 again. Do you agree? Yeah. Do we have agreement? This is a 2 cycle. Yes. Anyone objects? Have I made any typo? Okay. Yeah, so Berend says yes. Do you agree with the Berend? Anyone has any questions, any doubts about this? Okay, should I move to the next example?
Sure, I'm ready to move on.
Okay, and do you agree with us, George? What's your verdict? This is a 2 cycle.
Yeah, I think with two elements, it's really crystal clear. There isn't room for it to be anything else.
Yeah. Okay. Good. So here's another example. This sigma 2 tilde, it basically leaves 1 and 2 unchanged, but then the change starts to happen from 3. So it takes 3 to 4, but then it takes 4 back to 3 again. Just follow the arrow. Okay. So therefore the claim is that this is a 2 cycle. Do we agree again? Same here. Okay. Yeah. Excellent. I knew it was work to go through these these diagrams to make it easy. Okay, so this is 2 cycles. Let's up the game in the gaming cycle stuff. Let's go to 3 cycles. Actually, here's an exercise. So I've given you examples. So the first challenge is that are there other 2 cycles in S4? If yes, the challenge is that identify all the 2 cycles of S4 and also identify how many disjoint 2 cycles are there, if any. Remember the definition of disjoint 2 cycle, right? I mean, this in general, the abstract definition. Let me go back again. You know, this. Okay, so all you have to do is identify the supports, and then you see whether their intersection match. Okay, so all good. There's something wrong here. Have I actually, I think my slides, have I deleted something? Because, I knew. Okay, so I think, let's see, there's something happening here. My other content, the other content of the slides are not showing up. Why is that? Let's see. What have I done? This will be painful. Oh my goodness. Let's see, restore this version. I think I must have deleted something before. I'm restoring, trying to restore. Yeah, so we should be back. Yeah, what happened was I deleted when I was adding things to with James. Let me stop sharing. I think it will refresh. Sorry for that. Am I still with you guys?
Still here.
Yeah. Challenge 1. Okay, yeah. Excellent. I'm glad, actually. I didn't know Google now. I mean, they must have had it for some time. I never used like versioning on slides.
That's nice.
Because I could go back to the version where when I didn't delete it, restore it. That was a savior. And it's very, very hard to, I mean, very easy to delete stuff when you are trying to add things. It should at least pop a message. Yeah. Okay, so can you see again the slide? I mean, it's loading.
Yes.
Yeah. Okay. So this is challenge 1. Was there any? I can see George. Was this any confusing or something like this challenge here? So the challenge is to identify other 2 cycles on S4 other than the previous examples, and then are there like I think there is a duplicate questions here. Yeah, maybe that's why you were looking, you know, because
No, it was just I had to get my eyes closer to the screen.
Okay. Yeah, Yeah, it actually makes sense. The question is asking whether there are. If yes, then identify all the 2 cycles of S4. And then the second question is how many disjoint. You know what the disjoint case cycles are in the abstract. In the definition, go back to slide 1. How many disjoint 2 cycles are in S4? But first, you need to identify all of them, ideally, and then find out. Okay, so we go. This is strange. It's like hasn't it refreshed? Okay, maybe I need to share again. Yeah, sorry for that. It's probably because of caching or something. Let me go back again. All right, let's see. Why is it not? I think I might have to go incognito in another window for the latest update to come in. I promise we'll finish on the time. Sorry for this. Let's see if I can open an incognito. Yeah, so now it works, I believe. So we were here. We'll move next to concrete examples cycle 2. Okay, yeah. Okay, I'll close this. Okay, so let's see. Chrome tab.
Bob is asking, what if a permutation has more than 1 2 cycle, like 1 swaps with 2 and 3 swaps with 4?
That's something we'll say when we see about the uniqueness of the cycle stuff. We'll come to that. But hold that thought, and I'll thank you for you to go and think about it, actually, to see.
Yeah, I see a new slide.
Yeah, let's see. So this was why? It doesn't seem okay. What I will do, sorry for this. What I will do, I think I will just download the slides and upload it here. Plan B, because the browser doesn't seem to. I think it's probably to do with the caching stuff. But then if I delete all the stuff, is any other comment on the thing on there? This is very important. This thing, because in the next session you will learn how to compose 2 cycles, for instance. And you will learn very important properties of the cycles, in relation to the other permutations that are not cycles. We'll come to that. And I think once you work out with them, you will actually get to those conclusions yourselves without me saying. Let's see, concrete. Yeah. Okay, slide. I'm going to upload it. Sorry, guys. Group theory lecture. Yeah, it's uploading. We were not here. We were here. 21. Okay, yeah. So now there you go. It works. So we were here. So the next, so we were in the example of 2 cycles. So now we are going to 3 cycles. Okay, in S4, let's stick with S4. See what it gives us. Okay, so let's consider S4 again, but let's consider the following permutations in 2 lines together with the diagram, with a new diagram. Okay, so again, let's call it sigma tilde 1. What it does, it takes 1 to 2, 2 to 3, but then it takes 3 back to 1 again. So, and then it leaves 4 untouched. Okay, so using this diagram here on the side, this is much more easier to see this. It takes 1 to 2, it takes 2 to 3, and then it cycles back again. It sends back again. It goes back again to 1. So you start to see why the naming cycle and these things. So it goes again. Okay. So the claim is that this is a 3 cycle. Okay, with the supporting, with the support 1, 2, 3. You'll start. This is one of the reasons I'm trying to do this, because this then, as you go through this is already making the cycle notation very obvious. For those of you who already know the cycle notation, because you can see this, you will see this in a minute in a more obvious thing. Okay. So this is a 3 cycle. That's my claim. Do you all agree? I think I disappeared. I just zoomed this. I think I put us on the top, George. But the only thing, I cannot see the chat. Can you see the chat? Am I still on, by the way? Okay, let me exit the chat. Am I still on? Somehow I cannot hear George.
Oh, I'm sorry. I had muted myself. I'm sorry.
Okay. Is it better this way? This slide, is it bigger now, like this?
It's a little bigger.
Okay, yeah. So I cannot see the chat. I was saying I've zoomed this. It seems this is a new feature I discovered from Crowdcast. Does anyone have any doubts that this is a 3 cycle? We are all on the same page. Can you see the chat? If there is anyone who doesn't agree, or do everyone agree?
The chat as of now is quiet.
Okay. Can someone, who from the chat, a brave person, who agrees this is a 3 cycle?
Okay, Berend agrees.
Okay. Anyone else?
And Bob.
Okay, so we're all on the same page. I assume, George, do you agree? This is a 3 cycle?
Yes, the little picture, the diagram on the side makes it crystal clear.
Yeah. Okay. So here's an example. So this is the first example. So this is a first example of a 3 cycle. And here's a second example of a 3 cycle. Okay. So in this case, this, I claim, this takes 1 to 2, 2 to 4, but then 4 cycle back again. It untouched. It leaves 3 unchanged. It takes 4 back to 1. So the claim is that this is a 3 cycle as well. Do you agree? Or have I made any typo? So it takes 1 to 2, it takes 2 to 4, but then once we get to 4, it takes 4 back to 1. It doesn't do anything to 3. So we ignore 3 because nothing happens to it. Okay. So this is a 3 cycle.
So for this one, the support is 1, 2, 4.
Yeah. this is actually a good example for you to see. This one is 1, 2, 3 for you to see that cycles don't have to have like the right sequence in the thing before the eyes, like like this, That's why I was saying you have to ignore things that are not unchanged. Just ignore them. They don't exist. So just follow the things that when changes happen. So you skip through things that when changes don't happen. Okay, so now, just like when in the case of 2 cycles, the question is, are there other 3 cycles on S4 other than the previous 2 examples that we just went through it? Okay, and the idea, the challenge then is to identify all the 3 cycles of S4. And the second question is, how many disjoint 3 cycles are there? Okay. And the third challenge is identify all 4 cycles in S4, if there are any. Why not? S4, 4 cycles, or is it nonsense? Well, have a look. And how many are disjoint, if any? And the final question is, are there 5 cycles in S4? Okay. If you look at the foundational stuff, you should be able to answer this. If you answer this, then it means that you have had a grasp of this. Because in the next session, what we'll do, we will we'll start making things a little bit more complicated. For example, multiplying cycles, for instance, and also decomposing cycles, especially decomposing permutations into cycles. I don't want to give away because there is a theorem actually to do with this. I'll say it ahead already. We will come back to this, that any permutation can be decomposed into product of cycles. Yeah, we'll see exactly how and what type of cycles in the next session. Not worry about that. For the time being, it's just for you to be familiar with these notions, the notion of cycle, and go through these exercises, and you will be fine. And now we'll go back. Yeah, go ahead, George.
In the chat, Berend is claiming that none of the 3 cycles are disjoint.
Okay, well, you can argue that in the study group with George. I hope you enjoy it. You join it, and then you can bring and put your case. You still having the study group session next week, right, George?
Yes, unless you want to speed things up and have the lecture every week.
No, I think we are fine for the time being to do this. Maybe once August comes in, maybe we can then do like, especially in the matrix group section, maybe we can, because a lot of you have seen the matrix group stuff, so maybe we can do weekly once we get there. So it's fine. You can have a study session. It's also a way of dragging my feet because, as I said, this might be my last session. My last course.
And as always, Berend now wants to retract his bold claim.
Okay, well, that's fine. Maybe you will change your mind again. The key thing is it's very hard to do it on the fly, so no worries about it. Go think about it and go through the exercise, and go write and these things, and then bring it to the study session with George, and then you take it from there. So now
it would help to. I think it would help to work it out on paper a little rather than try it in head.
Yeah, that's why I'm giving these toy examples, because once you get familiar with this, these are like feasible to do on paper, as opposed to S 1000 or something. Yeah. Okay. So this brings me to the final thing, which is the cycle notation convention. So this is, as I was saying, I avoided to do this. Normally, when people introduce cycles, they introduce the notation first, and then introduce the notion of cycle. I think doing it abstractly, I'll ask your verdict in a minute at the end. I think it was better to do it and then introduce the notation at the end. So let's. I know it's very small. Can you guys see? So let sigma tilde be a permutation. So let it be a K cycle, okay? because it's a case cycle, it means it has a support. Okay, the support of the case cycle of this sigma tilde be A1, A2, A3 to AK, because it's a case cycle. Okay, now by convention, what in books, in textbooks, what people normally write, obviously they don't write sigma tilde. This is just my notation, abstract notation, to make it easy for you to understand. This is how they write it. So they put this thing inside this bracelet, or how do you call this? This is a bracket, right?
Parentheses.
And then, yeah, parentheses. Yeah, so they put these the supports, these guys, in the parentheses. So this is what they denote this permutation. This sigma tilde, the thing that we've been calling sigma tilde. This is how in textbooks it's been notated. You know, you just write the support in the parentheses, in between the parentheses, without space, without comma. You just write them. So here's an example. So one of the examples, one of the two cycles, for example, like this one, you know, the one that takes 1 to 2 and 1 back to 1. We just write 1, 2 inside the parentheses.
In the chat, Barry is asking if we can return to the definition of a disjoint cycle.
Yeah, I'll get back to that in a minute. Let me just go through this. So I guess this is clear here. This notation stuff, you know. So all you do is to identify, to write. So in this cycle, for example, the map, the permutation is written inside the parentheses. You know, in this case, you know, when you see this 1, 2, 3, just insert this. This is what's happening. You know, it's what's happening is that 1 goes to 2, 2 goes to 3, and 3 goes back to 1. This is it. So they don't write sigma. So I hope by doing it this way, you know, you could first of all understand the abstract definition of cycle, and then it's more natural. Naturally, you came to the notation. The notation becomes now makes a little bit more sense, as opposed to like you know, being exposed to it as rule-based stuff, like many normal introductory stuff would do, which is because they start with the introducing the notation first, which looks more like rules and all this stuff nonsense. Yeah. So this is it. Do you have any doubts about this notation before I go back to Barry's thing, the notion of a disjoint cycle? George, is there any question on the chat? Because if I exit the
no further questions.
Okay, good. So it's thing. So this is the notation that we will be using. Okay, so we will write this the permutations in the thing inside this parenthesis, you know.
Yeah.
And then it becomes obvious that we are talking about this. Okay.
I think the little diagram on the side really makes it clear.
Yeah. Yeah. So it's abbreviated like this. Okay. It will be then it becomes very clear. You will see once you start doing, you know, multiplications and these things, you know, on a term of cycles, you know. Okay, so let me go back to what Barry was saying, the definition of disjoint cycles. So it means the support, in this case, the thing, they don't have anything in common. It's empty. In fact, we can actually look at the two cycle examples and ask the question. For example, these two, are they disjoint cycles? Is support of this, is this set intersection with this empty? So they are disjoint cycles, right? Is it? By definition.
Yeah, I think the disjointness doesn't even matter about the cycle. It's that the subsets are disjoint. Null intersection.
Yeah.
Oh, Barry has a further question.
Okay, let me exit this. Yeah, what was it?
Haven't you been saying if a particular cycle is itself disjoint? you need a pair of cycles to talk about disjointness.
Yeah. And isn't that what we have? Because I'm saying these are like two cycles. So this one is
again, you can think of the cycle as being disjoint from the remainder of the set, which is not moving around.
Yeah. Let me exit this screen so I can actually see the chat. I forgot. There's a challenge that I would like to put, but the challenge is big enough. I don't need to zoom the screen. I hope I label the challenge. So now this is very important. Actually, you will find if you do this challenge, I think if you were to pick which challenge, I would definitely say put this one of the challenges that you will try to do, because you will see something very interesting in this case. So identify all the cycles of S2 and S3. It doesn't matter whether two cycle or whatever. And then identify all the disjoint cycles. Try anyway. Yeah. You'll see something interesting in these two use cases. I claim anyway. So if
okay, Barry is asking, didn't you ask how many disjoint cycles S4 has? Do you mean how many disjoint pairs there are?
Yeah.
That's a good clarifying question, Barry. Thank you.
Yeah.
So I think maybe the concept to hold in mind is mutually disjoint cycles.
Yeah. I guess that's the thing. This is where the framing of the thing can make a difference. Yeah.
But I maintain that it's actually merely a question of subsets when you want to count them.
Yeah. In the next session, we'll see actually there is a downside with all this cycle stuff because it's not, the notation is not unique. You will see some cycles that they are written different, but they mean the same thing. They are the same thing. You probably, when you go through some examples, you will come to that conclusion. We'll come to that because I don't want to. Yeah, I don't want to confuse you for the time being. But this is all. This is all things that you should bring to the study session.
Okay, yeah. Dimitri is pointing out the subtlety that for 3 cycles, there are distinct cycles corresponding to the same subset. Yeah.
We'll come to this in the next session. We'll see all this the thing when we talk about, especially when we're talking about the composition stuff.
I guess my point was that I was just thinking about the support. And Dimitri is right that for k greater than 2, the same support can have different cycles.
We'll come back to this on the thing in the next session. I don't want to put the head, but it's good discussion point. Good, you are thinking about good point, good discussion points. And it will be interesting if you take this to the study session and come up with the examples and counter examples stuff on the thing on this discussion. But it's all I ask is try to feel comfortable with the notation, especially the cycle notation stuff, because then we'll start adding some stuff, and also there will be some theorems that maybe some of them we will not. It will be hard for you to even try to prove because we need the notion of action, for instance. So we'll see how it goes. Yeah. Okay, so does anyone have any question or? Does anyone have any question?
Let me on Zoom. No, not since Dimitri and Barry's questions.
Okay. Okay, so yeah, so this is the session 11. So let's see. I'll try my best to not skip the next session because of the pressure for the measure theories to release you guys to go and for those of you who are interested in the measure theory and functional analysis stuff to be able to have more time in hand. Okay. Any other comment, George? All this approach of starting defining the case cycle in abstractly versus starting with the with notation first and then defining the notion of cycle.
From my point of view, I remember the first time I saw the notation out of the blue, it was confusing.
Yeah,
that was me. So I agree that having the abstract definition kind of makes it clear what it is that the notation is notating.
Yeah.
So I like now more and more, I like the idea of talking about the support, and then the notation just puts the support into the parentheses.
Yeah. Yeah. I'm glad. Okay, so the verdict is positive because this is exactly one of the things that I decided to the way I thought it much easier to understand. A lot of this stuff that I do is like it's my thing is like I wish I was taught these things that way. So a lot of the inspirations that I have is like I do it the way that I would like all these things when I learned them to be when I picked a maths book or the professor whoever was lecturing.
Barry is saying that he recalls that the notation for 2 cycles was introduced first.
Ah, okay. And how was it? Wasn't it a bit confusing to start with? Especially when you start. I mean, as you go with more examples, but then you have to drink a lot of examples, right? for the thing to start to sink. Yeah.
Not confusing.
But then when you start to go with the case cycle, especially when the thing the placing of the objects are not sequential, for instance, it becomes a little bit more.
No, yeah, like I keep saying, I like the little diagram, and the diagram also makes it clear why it's called a cycle, because the diagram just goes in a circle without any twists and interconnections.
Yeah, like this guy here.
Barry found manifolds and such things more confusing. So Barry's
okay.
on the opposite side of the divide from me. I find the manifolds crystal clear and struggle with the algebra.
Well, it's one of those things, they say, people have more algebraic mindset, others have more, geometrical mindset and these things. So it's really,
Okay.
What happened? Is saying stage empty?
Yeah, I still hear you. I don't know
Right.
what this looks like to anybody else. Dimitri is also finding algebra more intuitive and topology kind of cloudy.
Okay, interesting.
Okay, now
I must have done with something with the settings.
maybe
Stage
when
control.
you stopped sharing the slides, it changed modes.
Right.
Now it seems to flash between showing you and me.
Okay. Okay. So it's going back to the normal. It's one of those things. They have like icons, and they expect people to understand what the icons mean. It's like, yeah. So yeah, Dimitri, I also find algebra and topology kind of cloudy. Yeah, that's interesting. Yeah.
Maybe I'm in the minority then.
I mean, there is always from both sides. There is depending on which spectrum you are. I tend to be in the middle. I find both things very very fascinating. Both things, and actually, this is very interesting to see how, especially in this functional analysis stuff, because it's a kind of an intersection of both. You will have a bit of topology there, analysis, and yeah, it will be interesting to see.
Barry is reassuring that there are plenty of continuous mathematicians, so I'm not alone.
Yeah, well, didn't David Hilbert said something about don't what was it about the Cantor's paradise? The paradise that Cantor. There's a what's the quote? I forgot.
Don't let anybody throw us out of the garden of Cantor's paradise.
Yeah, exactly. Yeah. And he was one of the greatest, saying, when all this debate, in the thing in mathematics between intuitionist versus
And Dimitri made a little joke that there's a continuum of continuous mathematicians. I like that.
Yeah, it's always, and it's saying this the thing. There's also a joke that says Monday to Friday mathematicians are formalist, but at weekends they are Platonist.
And Berend is saying, I guess that's why you were a mathematician, Bamborde, right in the middle.
Yes, we try to take. I'm a bit along the David Hilbert school, with a bit of touch of maybe a bit of influence with the Bourbaki.
Yeah, I mean, I'll go right off the deep end and say I didn't really understand the algebra until I studied the algebraic topology.
Yeah, but then Bourbaki itself, they were not a lot of their books. They didn't include all these categorical stuff. There are a lot of opinions to why that was. Maybe the theory wasn't that developed too much, but or maybe they were too much into set theoretic centric foundational thing of mathematics. Yeah,
I think it really has to do with who the members of Bourbaki were and what their interests were.
Also, yeah, that's yeah.
Barry says category theorists are all crazy.
Well, we will we have something planned on category theory, applied category theory for computer scientists. So Barry definitely will love this. And then we'll have on top of that homotopy theory, homotopy type theory. So there's a lot of interesting stuff coming up, and we'll have, after the category theory itself, we'll have something on algebraic topology, because you need the notion of functors and all this stuff.
And Dimitri is on a roll. He says that's a bit too categorical.
This is the thing with maths. We can make a lot of how do you say
in jokes.
In jokes, yeah. But then only people within the tank that will understand the joke, right? If you talk to a mundane person, they would know what are you talking about? Why is this a joke?
It's very confusing to non-mathematicians because we don't use fancy Latin terms. We
Yeah.
use ordinary English in a weird way. Like everybody knows what a group, a ring, and a field is, but that's not
Yeah.
what we mean.
Yeah, exactly.
And the
Yeah.
category too.
Yeah, it goes to, there was the quote, I forgot who said it. I shared it a couple times. They say a mathematician are like Frenchmen. You know, whatever you say to them, they translate them in their own language, and it becomes completely something completely new, different.
Yes, that was the great writer Goethe.
Yeah, Goethe. Yeah, yeah.
Johann
I think it was him. Yeah.
Goethe.
Yeah. So yeah, does anyone else wants to add anything? I can happy to invite people on stage, or we can end it here and sum up in the next session. I will create a study group next week, George, and share it with you. It's very
Thank
important to go through some of the challenges, even if they are trivial and easy stuff.
And again, I encourage, and this is also for the people on YouTube, if you're in a different time zone, try and find somebody else in the time zone that you can study with, or talk to your cat.
Okay. I don't have anything else to add, George, unless you want to add anything. Otherwise, we'll just leave it here. And thank you, everyone, again for showing up. And yeah, we are getting there.
Yeah, the
Yeah.
pieces are falling into place. I'll
Yes.
make my little joke that unlike bicycles and tricycles, where you start learning on the tricycle because it's easier, with these K cycles, the 2 cycle is easier than the 3 cycle and on up.
That's a nice one. So on that note, on this great joke, I won't say anything else. We will just end here. And George, thank you so much, and thank you, everyone. And yeah, we see you again in the next session.
One last from Berend: always go for the empty set.
Okay, guys, thank you so much, and have a good weekend, everyone.
Okay, bye.
Okay.
How do I leave the stage?